you can continue your feasting. I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students and just ask that you'd bless our class today, Lord. In your name I pray. Amen. All right, so as you guys remember, we were talking about what? Quotient space, right? Quotient topology. So I'm going to continue. I had one more example to glean from this. And then I'll recap the theorems from the other book, actually. So what he does is he looks at x equal to the unit square, right? And he says let f be a function from x onto the torus. And so what's a torus? Yeah, that's the donut. Now, to be fair, that is true, but, well, visualizing this directly, this is a subset of what in his construction? C cross C, yeah. So I don't disagree that it's a donut, but it is a donut sitting in a four-dimensional space, four real-dimensional space. But this is much, I mean, you could, I suppose, make a function going from the unit square to a physical donut, right? And use the geometry that is kind of obvious once I write down the map. What is it? He says f of st equal to, what is it? E to the 2 pi I s e to the 2 pi I t, right? And he says that the level sets of f are singletons inside the square and pairs of opposite points on the interiors and boundaries of the intervals of x. All right, so let me try to talk about that. So if we put, let's see here, 0 less than or equal to s less than or equal to 1, 0 less than or equal to t less than or equal to 1, right? That implies 0 less than or equal to s, 0 less than or equal to 2 pi s, yeah? Less than or equal to 2 pi, and 0 less than or equal to 2 pi t less than or equal to 2 pi, right? So the point is that the angles, if you like, you could call this one, say, theta, and you could call this one beta, right? If you look at the angle theta and the angle beta, it's ranging from 0 to 2 pi, right? So if you look at the inverse image of, st, excuse me, of e to the, let's say I theta, e to the I beta, what do you got? Because that would be a fiber of the map, right? And the theorem we're using, hooray! Okay, good. I was worried you're sick. As you know, many have become sick. Ah, okay. So I was trying to go through the final example in Gamelin that we hadn't got to yet. And I'm using that theorem that I covered last class, which was, what was it? If we have x and y compact Hausdorff spaces, right? F, a mapping from x to y, continuous, right? X and y, what were they? Compact Hausdorff, then what? What was the deal? X mod, the fiber equivalence, is homeomorphic to y. I think I have, again, failed to say something about f that I was supposed to say here, otherwise that's not true. Hey, what have I? It better be continuous surjection, right? If it's not onto, well, yeah. And that, what's the equivalence here? This is the fiber equivalence, right? In other words, x is equivalent to y if and only if what? F of x equals to f of y. So this is the so-called fiber equivalence, yeah, that partitions the domain into disjoint sets, and as such can be viewed as an equivalence. That partition can be viewed as the partition afforded to the equivalence relation, this fiber equivalence. Anyway, the inverse image of the singleton is what? He says there's two cases. It's either, what is it? It's either just, oh man, let me be lazier here. 2 pi s, yeah. We know that this is an arbitrary 2 pi t. So if I do that, then you can even see it easier, right? You get what? St. If what? So if St is in the interior, like that, then that's the only thing in the torus that's mapped to is just e to the 2 pi s, e to the 2 pi is, and e to the 2 pi it, right? But what happens if, say, s, let's see, what's the other case? We could have something like, let me just write it separately. What would be the inverse image of, say, 1 e to the 2 pi it? That would force s equal to what? In order to get e to the 2 pi is equal to the 1, what does that say about s? S equal to what? Say? Equal to some integers, right? But remember, s here is not some integer. It is stuck between 0 and 1. So we have two choices. S equal to 0 or s equal to 1. And so this is what? This is the set, let's see, s equal to 0 or s equal to 1. And what's the t? It's just t, right? And I guess I should say 0 less than t less than 1, yeah? If we're in that case, then it's just that pair of points, right? Likewise, if you look at the inverse image of, say, e to the 2 pi is and 1, what does that give us? I think it would give us s 0 and also s 1. And this is given the condition 0 less than s less than 1, right? let me draw a picture of what's happening. What I'm saying is we're identifying what, like let me make this first one red. What points are we identifying on the square? 0t, 1t, what are those? That's like this and that, right? These are being identified in the quotient. We're connecting those points, gluing them together in the quotient space we're constructing here by the fiber equivalence. And what about the other one? These, right? Be like this point and that point, right? Gluing those points together. Let's see here, this one would be what? S0. Up here you've got S1. This point was, oops, victim of my own color coding. Let's see here. 1t, 0t, and then finally, what's the one case we haven't considered yet? Like a corner point, right? Where would a corner point map to? Pick one of the corners, any corner. What do you want to pick? Let's pick the easiest corner, which would be? Up, 0, 0, yeah? Where does 0, 0 map to? Zero, 0 maps to 0? No, you didn't say that. It was what? E to the 0, aka 1, 1, right? So the question then is, what's the inverse image of 1, 1? I mean, by construction, I mean, we already know it contains 0, 0, right? What else does it contain? Right, so we're essentially just solving e to the 2 pi is equal to 1 and e to the 2 pi it equals to 1. We're solving those simultaneously. And so that means that s and t are both integers, but because of where they're coming from, that means we can either have 0, 0, 0, 1, 1, 0, or 1, 1, which is, of course, the four corners of the square. Those are in the inverse image of, oh, shnikes. Is that right? Have I messed this up? No, that's fine. It's fine. So these are glued together, right? And that's the thing I tried to illustrate with a crumpled sheet of paper last time, right? We take a paper, we can connect the two, like the length together, and then if you could somehow smoothly deform it and connect the width together in the same way, then that's a torus. Now this torus, it seems to me, is well, that's a good question. Where is the x mod tilde? Like, where is that? Is that in R2? Is it in R3? It's homeomorphic to something that's a subset of C cross C. Where is it? I think that's not a good question, actually. It is the quotient of x by tilde. I mean, that's what it is at the moment. But we could look at it as a subset of C cross C, right? Can you guys tell me geometrically, like, what would this also be homeomorphic to? What if, I mean, I could draw a picture, right? Don't make me give you the map, but I think we could all agree that if we could come up with, you know, one of these deals, right? And if you, say, define this angle to be, say, theta, and then relative to this, say, pick that point and call this angle like that beta. You know what I'm saying? Like, you take a torus, you say one angle around the central axis sweeps out to beta, and then you take a circle that's vertical slice of the thing and sweep up to theta. This would be a way to construct the torus as a subset of 3 dimensions. It seems to me that should also be homeomorphic to either one of these. And more matching what we would usually geometrically mean by torus, right? Just donut. What's the homeomorphism of, can you tell me? I don't know, fun question. This is not in the book or anything. I'm just making trouble at the moment. If you had to map this point, I mean, you want to map it to what? 2 pi s, right? 2 pi t, quote unquote. I mean, those are the coordinates on the torus. How would we convert those to points in 3 dimensions? I mean, you got to pick a size, right? Like, how big is the radius? Like this, right? Versus like this. And then it becomes a relatively straightforward problem of 3-dimensional coordinate geometry to come up with the formulas in terms of r and a and the angles that you've been given, 2 pi s and 2 pi t. You agree? Or you disagree? You seem worried. Oh, without, yes. Oh, yeah, I don't know what the formulas are right off the top of my head. I'm just saying it is a straightforward, but, you know, geometrically somewhat involved process to come up with those formulas. You want me to do it? I mean, I visualize it like this. I've got this triangle, right? This angle is theta. This radius is r. This point right here is something like, how's it go? I'm just putting this be z-axis. This is x, this is y, yeah? So this point would be something like r cosine theta, yeah? R sine theta, and 0, because it's in the xy plane. So that just gets me this point here, right? That's this point. And then I have to imagine building on top of that. I'll draw it in its own little, I'm trying to get up to this point here, which is angle beta, like that. And so that, in my picture, this is that point again. Now I'm thinking of this being a vertical circle. And so this is still, I mean, that's not the z-axis, but it's parallel translated. The z-axis still has the meaning of z-coordinate. And, well, this is, goodness, for lack of a better notation, r-hat direction. This is the z-hat direction. R-hat being, you know, cosine theta, sine theta, 0. So how do I get that point right here? Seems like I'm interested in r-hat what? R-hat cosine beta, yeah? Plus sine theta z-hat, yeah? So if I take that and not theta, but beta. If I take the thing I just wrote in black and I add it to what's in the blue above, that should get me to the point, like this point right here on the torus. And so this is how I would construct the parameterization of a torus, actually. Here it is. X. Oh, bad choice of letter. R. R of theta and beta equal to, what we got? R cosine theta. Remember, r hat is what? It's cosine theta, sine theta. So that gives me a plus, you know, I need a what? I need a what here? What? I need an A, because that's how big that circle is. So r cosine theta plus A cosine theta, cosine beta. That gets me the x. Oh yeah, because this is z hat. Doesn't interfere. It's got nothing to say about x. And then, comma, what's the y? R sine theta plus a, how's it go? Sine theta. I see I could have written this more elegantly, right? Cosine beta. And what's my z? A sine beta. Let me rewrite this a little bit because it bothers me. So I could rewrite this as r plus a cos beta cos theta, comma, r plus a cos beta sine theta, and then a sine beta. So if you map 2 pi, this e to the 2 pi is, e to the 2 pi it to r of, instead of this, I should do what? R of that, right? I'll put a vector on it because, hey, we haven't had any vectors in here yet, right? And I think that would define a homeomorphism of the sphere embedded in C4, C2 cross C, and the standard geometric torus of radius, inner radius r, and, well, small radius a and large radius r. Yeah? Does that make sense? Is that a homeomorphism? So you want to use topological tools to construct it so you don't have these pesky questions I just raised? More categorical. Mm-hmm. Ah, very good, yes. I guess what I'm trying to say is that's good. That's actually how we're going to do things for the rest of today. But I just wanted to explore this because I think it's kind of, when I was doing these things, no one ever did this kind of thing, and it was kind of like, why aren't we doing that? Well, the reason we're not doing that is because it's clumsy. Yes, it's geometrically lucid, I think, clear geometrically what this is, right? But it comes at great cost in terms of like actually proving these stupid expressions are in fact, that they're continuous is kind of, they're products and sums of continuous functions, which are continuous. Each component's continuous, so it's continuous. The pickier thing is like the bijectivity. Like how do you invert this, right? So that's kind of a fussy question, but it basically boils back down to the fact that we chose angles such that the angles are not degenerate. All right. I lost my thing. I don't know where my rag. My rag. It's sad. Oh, speaking of sad. Oh, did you already? You got this, right? Okay. So in Calculus 3, when they ask me how do you parameterize a torus, I mean, this is what I should do, right?
What's the probability of your Calc 3 asking how to parameterize?
Well, there's one very important question to know whether or not they're going to ask me that. The question is, in the homework, is there contained the question, how do you parameterize a torus? If the homework has that question, then it's very, very probable they'll ask me about it. If it's not there, well, I don't know. It's harder to say. Okay, so I wanted to look at a silly example. What if we took all of our, oh, wait a minute. I was about to get into trouble, because what does the theorem that I just erased say? Compact Hausdorff, right? And I was about to try to play the same game, but with like all of R2. No. No. All of R2 is not compact Hausdorff, is it? Hausdorff, yes. Compact? No. Okay, so let me try to say things over here in the other book. This is chapter 3 in, Yannick's Topology, right? And I will, go back to the beginning here again, because I think it helps emphasize the what's going on, right? So definition, what's quotient? Definition of quotient space, all right? What's his definition? He says, let X be a topological space with equivalence relation tilde, a set U, a subset of the quotient space, X by tilde, is called open. In the quotient topology, if what? Pi inverse of U is open in X. All right, so to be clear, the notation he uses is X by tilde. It's the set of equivalence classes, right? It's the set of X, such that X is an X, where this equivalence class is Y in big X, such that X is equivalent to Y, right? So the quotient space is a set of equivalence classes, and we judge a space inside the set of equivalence classes to be open if pi inverse of that set is open. Now, what is pi inverse of U? Right, such that pi of X, which is equal to the equivalence class of X, is an element of U. So this notation, pi is a mapping from where? Pi is a mapping from big X to the set of equivalence classes, right? To the quotient space, as it's called. So this is the same is there something wrong? Okay. I mean, this is the same definition that we looked at last time, right? Good. And I like that he gives some pictures. He says, let me read what he says here. He says, just as we have for notions of subspace, disjoint union, and product, a simple mental image on which we can base our intuition in the beginning, what's a simple mental image, he says, is to just imagine the equivalence classes as themselves as points, right? He says, but though these equivalence classes are points of the quotient space, that's not enough because our intuition demands a geometrical picture for the quotient space, which the points of the space are really points, quote unquote, in the geometric sense. So I think he has some pictures here He's like, if X up here has, these as, these some typical X4, here's X3, X2, X1, whatever, then you can view that in some sense as being down here, right? So we can kind of envision projecting these whole things down to just this line. Something like that, maybe. Or here's another picture. If your if your total space was like 3-dimensional, right? And your fibers, well, if your equivalence classes were like vertical stalks, right? If your equivalence classes were like this, right? Here's another one over here. Then maybe a good model for the quotient, if these are the equivalence classes, right? So here's like equivalence class of X, equivalence class of Y, equivalence class of Z. Maybe a good, a mental picture for what that quotient is of that 3-dimensional chunk mod that equivalence is like a plane, like a little, like down here, we can envision the quotient like this. And I'll just use X bar, Y bar, and Z bar because I'm tired of writing brackets. Okay, so this would be a picture, a mental picture for X mod tilde if this is X. The larger point, like we were talking about last time, the idea with the quotient space is you're identifying points in the original space as being single points in the quotient, right? This is what we're trying to describe as many different which ways as we can. Now, oh man, I'm getting the dust on my book. No. All right. So at this point, I'm going to rewrite the 3 major theorems we covered last class. I'm not going to prove them again. I'm just going to state them, all right? So note, he calls them notes. Note number 1 is what? Maps on quotient spaces. He says, let me draw a diagram. You've got X up here. You've got X mod tilde down there. And you've got Y over here. All right? So if we study a function from the quotient space to Y, and we study the projection map from X to the quotient space, then of course over here we have what? We have F composed with pi. And what does note number 1 say? It says the following. It says a map F from X from the quotient space to Y is continuous if and only if what? F composed with pi is continuous. All right, I'm going to try to not erase that because we're going to come back to it, okay? Note number 2, and I'll draw the picture. We've got Y down here. We've got X up here. We've got X quotient space by the equivalence relation tilde there. Of course, we've got a pi here. We've got a phi down here, and then a big phi and a dotted big phi. So what's the deal here? What's going on? He says there's no corresponding universal criterion for the continuity of a map going from Y to the quotient of X by tilde, but the following trivial observation is often useful. If there is a continuous map if there exists phi from y to x such that what? With phi equal to pi composed with big phi, all right? Then what? Phi is continuous. And then he does more than that, right? He says you can be less greedy, even if you can just do that locally, that gives you continuity of phi, right? And he describes what he means by locally. He says if for every y and y, there's a neighborhood u for which there's a continuous map phi u from u to x with pi composed with big phi u equals to phi restricted to u, then phi is of course continuous. Let me put the local version of that picture next. He's like, okay, so if you have a, if there's a global phi like this that composes with pi to give you back phi, little phi, then that makes phi continuous. That's one thing we can do. The other thing, though, is you can be, if instead you have, forget my letters, u and a phi u, big phi u, and still dotted, x pi, let's see here, x mod tilde. And down here we're looking at phi restricted to u. Each y in y has neighborhood u such that. All right. If I have what's in the blue box, if at each point in y I can find a local phi, big phi u, such that it composes with, sorry, I forgot to write my composition condition, pi composed with phi sub u equals to what? Phi restricted to u. Yeah. So if you can do it, if you can find more of them, like one for each point like that, then that also suffices to, you can piece it together and get continuity of all of phi. I think I proved both note 1 and note 2 last time, but not the local version. Okay? No? You guys don't remember? Do you want me to translate? Here, I'll translate. In section 13 of Gamelin, we looked last time at, let's see here, 13.2, let X be a topological space, let tilde be an equivalence relation on X, let pi be the projection map. A function f from X mod tilde to a topological space Y is continuous if and only if f composed with pi is continuous. That is note 1. Note 1 is theorem 13.2 we proved last time. And then 13.3, let f be a continuous function on a topological space X to a topological space Y. Let tilde be an equivalence relation on X such that f is constant on each equivalence class. Then there exists a continuous function g from X mod tilde to Y such that f is g composed with pi. So to translate here, Wait a minute. Maybe that's not the same. Oh. Yeah, the map's going the wrong way. That's not the same one. Huh. Maybe note 2 is new. For some reason, I thought it was the same. Well, anyway, that doesn't matter. Can we prove note 2? What do you guys think? What's the claim? If there exists phi, big phi, such that little phi is pi composed with big phi, then little phi is continuous. What does it take for little phi to be continuous? Let's not worry about the local version. Let's just focus on this one. This is the claim. Phi is continuous. What's that amount to? We need to show what? Yeah, phi inverse of open is open, right? What does that involve? Oh, but we know that. Yeah, we know that. Oh, we're given that pi and big phi are both continuous. Okay, so phi inverse of, let's say, where's phi map to? Here, right? So let me call it. I don't know. What do you want me to call the set over here? S for set. There we go. So phi inverse of the set, which is actually an equivalence class of the set of equivalence classes, right? Because it's in here. And so you're telling me that we're given that this is equal to pi. I feel like we did this last time. I don't know why. Right? But then by properties of set composition, right? I mean function composition in inverse images, that's what? That's phi inverse. Man, I feel like we did this pi inverse of S. And
pi inverse of S is open because pi is a continuous map.
so this is open by continuity, by pi continuity.
And then the phi inverse is also open
By the assumed continuity. Well, we didn't assume that.
That's what it has in here. It says if there is a continuous map.
Oh. So I just didn't write continuous. Well, that's going to make it really hard to prove, isn't it? It does seem like it would be nice to know that, doesn't it? Yeah, if we know phi is continuous, big phi is continuous, then we're done. So that's in his note. Okay, good.
Yeah,
good,
so
good.
I think
All right.
the point is saying that we can construct a small phi by looking at these composition maps, as opposed to trying to just construct it correctly.
Hmm.
It's a little bit, I don't know, it's a little bit trivial, I think, but
Mm-hmm.
I don't know what it means by
Well, that he means that there doesn't exist just one overarching continuous function phi. A bunch of them for each neighbor, like you find one for each neighborhood of a point, then you can take that data and piece it together to get the continuity of phi. And I think that, so we can somehow, continuity, if we know that, maybe this is a theorem we could prove, if we know that the restriction of a map is continuous for a cover with respect to a cover of the space, then that implies continuity of the map for the space. I think that seems like a reasonable claim. I mean, the U's can, I think the U here could cover the, I mean, it says each Y has a neighborhood U, right? So the U's cover Y. Okay, I'm going to stop talking about this because it's not that interesting. Sorry. Now he starts. Now the next couple pages here, action-packed. All right, so let's go on here. So first of all, he says X path connected, or X compact imply that X mod tilde, that the quotient space is path connected, and the quotient space is compact. Why is that? Because pi, right, is the mapping from where? From X to the quotient space, and this is continuous, right? How do we know that the projection map is continuous? Essentially, we have defined the quotient space to make this so. The topology on the quotient space is defined precisely to make the projection map continuous. Right? And we know what? We know that the continuous image of path-connected sets is path-connected. And we know that the continuous image of compact is compact. What's going on with the speakers? And this is also a surjection, right? So, all right. But, warning. If he says this, and let's try to dig into this here. It's easy enough to read it. It's harder to understand. A necessary condition for a quotient space X mod tilde to be Hausdorff is that all the equivalence classes in X be closed. Need all equivalence classes in big X to be closed. So in other words, we need X closed. What's that mean? In other words, X complement by that is in the topology of X, right? Is that me? Was that you, King? That was not you. I thought I heard a computer noise over the speakers.
Yeah, I heard it.
Weird. Okay. So, why need equivalence classes in X to be closed in order for X mod tilde to be Hausdorff? Why is that? Well, one thing we can prove about a Hausdorff space is that points in a Hausdorff space are closed. And singletons in a Hausdorff space are closed. All right? You may recall that from when we were talking about Hausdorff. So, why would this be a problem? So he's like, okay, so if, let me write it out. Let's just digest what he says here. He says, if Y is not an element of the equivalence class of X, and Y is, an element of the closure of X, right? What's the problem with that? In other words, and what I'm trying to say is Y is a boundary point. His claim is that then X, the equivalence class of X, and the equivalence class of y cannot be separated in the quotient space. And they cannot be separated by disjoint neighborhoods in the quotient space. Let's try to picture it, right? So here's, let's see, I'm trying to think of how I can view this. Maybe this is y. Let's see how to view this. I don't know how to view it. Maybe this is y, and this whole like strip is x, right? So like I want to say that y is up here, all right? And y is not an element of that, but it's right on the boundary of it, right? And so why is it that boundary of that the equivalence class of x and y cannot be separated in x? Mod tilde. Can you guys help me explain why that is? I mean, it made sense to me when I read it, but I wonder if I was tricking myself into thinking I understood when I didn't really understand. Let's see here. What would it mean? What would it mean for these? Let's suppose that they're separated in the quotient. What would that mean? So that would mean that in the quotient, right? You've got x, you've got y. They're distinct points, right? They're distinct points by assumption because y is not in the equivalence class of x. That makes these distinct equivalence classes in the quotient, points in the quotient. Yep.
Can we think about it in terms of pi being a continuous map, then closed sets have to map to closed sets, and so if it's Hausdorff, or if the quotient map is Hausdorff, the quotient space is Hausdorff, that means that each of the equivalence classes have to be closed in the quotient space.
Mm-hmm.
So all of the points that map to the equivalence class in the quotient space have to be closed in X. And then all of the points in X mapping to that equivalence class would just be all of the elements of the equivalence class.
So you're saying use that the inverse image of closed is closed under a continuous map?
Yes.
So, okay, let's try that out. Pi inverse of oh, I see. So you're saying pi inverse of this is what is that?
That's all of the elements in the equivalence class of X, right?
Oh, yeah. Yeah, I'm sorry. I'm tricking myself, my notation. So it's just this again?
I think so. So
Yes.
if we assume that the quotient space is
If this is closed,
right, because we're assuming that it's Hausdorff.
then that says that this is closed
Yeah.
because pi is continuous. In continuous maps, inverse image of a closed map is closed under a continuous map. But by assumption, the equivalence class of X is what? y is an element of the closure of X, but y is not an element of X. Cool. I think that's better than what I was about to do. I mean, I was going to, imagine an open set around each being disjoint and then track back what it meant. And I think it would get, since y is a boundary point, that means that the neighborhood's close to y. The neighborhood of y contains, that being a boundary point means what? It's in some sense close to X, right? And that's gonna mess up my open sets that are separating the 2 points. But man, this is a much better argument. Thank you. Now, this is a necessary condition. Is it sufficient though, right? I mean, what I'm trying to say is, if your equivalence classes, right, are not closed, if even one of them is not closed with respect to the topology of X, then the quotient space cannot be Hausdorff, right? So that means, at a minimum, the equivalence classes have to be closed sets in order to get Hausdorff, in order to get a Hausdorff quotient. Is that enough, though? The answer in general is no, it's not a sufficient condition. But he lets the cat out of the bag. He says that if X is metrizable, then it's a sufficient condition. The proof of this claim is suspiciously missing from the book. I don't recommend we try to do that one on the fly. That to me sounds like something that's born of some deeper thinking. But there you go. And he gives this rather disturbing example of, here's this picture in here, you guys. These two, see, Mr. No. These are two different equivalence classes for the plane. If you take the plane and divide it up into these these graphs, right? This could be like the solution set to a particular differential equation is what it makes me think of. And he says that one of these, if you quotient by one equivalence class, it's Hausdorff, but by the other one, it's not Hausdorff. So and he doesn't say which one is which, or does he? I can't remember. He maybe says, but anyway, so keeping Hausdorff for the quotient is tricky, all right? And generally speaking, preserving properties of your space to the quotient is perilous, all right? It's not guaranteed, but we do have this, all right? Okay, so next section. Oh man, I'm going way too slow. I'm sorry, guys. I am so sorry. Oh, the CFAWs wore me out. So in the next section, he talks about homogeneous spaces, all right? And so just to get us started here, he talks about, what's a topological group? We talked about that a little bit before, right? What's a topological group? It's G a group such that what? Which is a topological space, right? It's got a topology. And what? Such that?